This is our ClimTip webinar series where we bring leading scientists, early career researchers from different disciplines who study climate tipping points in the Earth system. And ClimTip is, for those who are new, is a research project funded by the European Union on uncertainty-aware quantification of climate tipping points, from the science basis to the impacts. And today we have Johannes Lohmann from the University of Copenhagen to talk about early warning of climate tipping points in high dimensions in the climate system. And quickly to introduce Johannes, he holds a master's degree in physics from the Technical University of Berlin and Duke University, and he earned his PhD in climate physics from the University of Copenhagen in 2018. Since 2021, he has been an assistant professor at the Niels Bohr Institute, where he works with the physics of ice, climate, and Earth group. Yes, and since 2023, he served as a visiting assistant professor at the University of Tokyo, and since has returned to Copenhagen, as I understand, right? And now leads the 2 research projects on climate tipping points funded by the Independent Research Fund Denmark and the Willem Foundation. And with that, I'll give it to you, Johannes.
Thanks a lot for having me speak here. I'll talk about early warning of climate tipping points. I realized my abstract was a bit unfortunate in mentioning the word data-driven. So what I'm going to present is actually decidedly model-driven, but then to be applied to data. So it's not a purely data-driven method, and it's probably also not really should be considered a method because it's still kind of a bit of an early stage research. So it's a bit more of a heuristic for early warning. Anyway, so we're all aware that there's different elements in the climate system that we suspect will undergo tipping at various levels of global warming. And in this assessment, they give certain ranges for the different elements in the climate system. Some of these are quite large ranges, and for some of these elements, for example, the AMOC here, the assessed threshold is still a bit far away. But there's large uncertainty, and arguably for most of these systems, we don't actually really know whether realistic state-of-the-art models will actually produce a tipping point under realistic climate change scenarios. Often this is because the models simply cannot be run long enough until they reach an equilibrium. But what we do believe, and that's why these are being classified as tipping elements, that there should be a physical mechanism in the real climate system that would lead to tipping, and that is always some kind of positive feedback here. So we don't really know whether the models currently agree on a tipping point, but we, for example, in the case of the AMOC, we don't really know whether all models actually possess a stable collapsed circulation state, which is necessary for tipping. But we do believe that the real world actually shows the underlying salt advection positive feedback here that should give rise to a tipping. And this can be estimated from data, for example. So since this is the tipping element I will talk about most today, I will quickly reiterate. So the AMOC is part of the global ocean circulation, and in the Atlantic, it transports warm, salty water on the surface northwards, and where this water then gets cooled, thus increasing its density, and then convects to the bottom where it returns as a cold, deep ocean current to the south. Now, the feedback here is the so-called salt advection feedback, and that is because this AMOC circulation is importing as a net importer of salt water, which means that if you would strengthen this circulation, it will import more salt water, and thus this surface water current to the north becomes more salty. And since salt water is more dense, this will lead more easily, given a fixed cooling at the surface here, will more easily lead to convection, and thus strengthening this circulation here. And this is a positive feedback loop, because if you would, by some perturbation, strengthen the circulation, this will then lead to an increased saltwater influx into these convection areas, which leads to an increased salinity and thus density, and thus leads to an increased convection here in these sites. And this strengthens the AMOC again. And similarly, all of these signs here can be reversed. So reduction of the circulation strength would lead to a reduction in surface density and thus a reduction in convection. And this is then a kind of a visual cycle and can lead to a runaway effect. And this is then the tipping point. Now, we don't have very long direct observations of the strength of this circulation. But at least historical reconstructions of this circulation from other data suggest that this AMOC has been slowing down over the past millennium or so, and thus indicating that we are at least getting closer towards this tipping point. But if we don't want to wait until all models would agree on whether or not this will happen, it may be good to have some more data-driven tools that can identify from observations whether a tipping point is imminent. And to this end, we want to harness some general features of mathematical features of tipping points that relate to the underlying dynamical system that we can then estimate and measure from data. Here, I forgot to mention, there are, of course, now simulations with realistic climate models that actually do show an AMOC tipping point. For example, here under medium range climate change scenarios, where the model is simply run longer than they usually do in IPCC projections. And here on the right-hand side with a very strong freshwater forcing that it mimics the melt that we expect from the Greenland ice sheet here. But the point at which this collapse would happen is quite uncertain. That's the need of data-driven techniques. Now, to obtain these data-driven techniques, we have to sort of define what is our underlying mathematical object. And to this end, we imagine the climate to be a stochastic motion in some climate potential. Why is it stochastic? That is because there will always be some processes that we cannot really resolve with a model or that we cannot measure in the real world. For example, erratically occurring volcanic eruptions or very small scale turbulent motion in the atmosphere and the ocean. So we assume that there is some kind of timescale separation in the different subsystems of the Earth. And we decide by focusing on a particular timescale, decide to treat faster timescales effectively as noise and much longer timescales to be effectively parameters of the system that can be either fixed or they can vary slowly over time. So in general, we have this Langevin equation where we have our state of the system X, and this is governed by the gradient of our climate potential here. And then there is a noise driving term here. And now in the case where this potential here is nonlinear and it possesses both positive and negative feedbacks, you can get a system where there is competing alternative stable states. So if we take this potential here, which is the double well potential, you actually have a positive feedback here and a nonlinear negative feedback here. And so sort of the competition of these two gives rise to two stable steady states, one at roughly -1 and one at +1. And depending on where you start with your initial condition, you will converge to either or the other. Now, if you then add noise to the system, you can have a transition in between either of these two states, which kind of goes back and forth. But if you imagine the noise strength to be very small, then these transitions will be very rare. So even though it's not clear at the moment whether the noise in the climate should be considered small or large, most people think that the more likely scenario of a tipping point may not be a spontaneous transition to another state, but rather a gradual shift in the equilibria and eventually a destabilization of one of these states. So this is the more common archetype of a tipping point, which is the saddle node bifurcation, where we introduce the control parameter here, which then gradually changes the potential, the landscape of this climate potential until one of the fixed points gets lost. So if you have a small value here, you still have both a fixed point stable here, but if you increase the value of R, one of your fixed points becomes closer and closer to this saddle point here in between, and then at some point they collide and annihilate, and then you're left with only one stable fixed point, and this will then be the annihilation of this stable fixed point is your tipping point. Now, the reason why we can potentially predict this is that you also have an underlying change in the curvature of this climate potential here leading up to the tipping point, and this can be measured from fluctuations. So if you look at the fluctuations around the fixed point here, when you're far away from the tipping point, the walls of this potential are quite steep. So there's very small only fluctuations away from this fixed point, and they rapidly decay back to the fixed point. But if you're closer to the tipping point, the curvature of this potential decreases, and the fluctuations are allowed to sort of venture further away from the fixed point, and particularly in the direction of the saddle point, which will become important in a second. And then, of course, eventually, if the tipping point is crossed, you have to transition to the other fixed point anyway. Now, this is a pretty old concept called critical slowing down that has been around in physics for a long time, but also in the climate and ecology literature for quite some time. You can just envision now to modulate that in the real climate system, the parameter R is modulated over time because of climate change. And what you're trying to do is you want to measure over in a time series, how are these fluctuations around the moving equilibrium are changing. And what you will see is that because of this change in the curvature, the variance estimated in some moving window here will be diverging up, leading up to the tipping point, but also the autocorrelation will be increasing, and the skewness of the distribution towards this unstable fixed point here will also be increasing. This has all been known in recent times. More focus has been devoted into not simply measuring simple quantities like the variance and autocorrelation, but rather directly infer the underlying restoring rate of the system, for example, because in what I presented now, I'm just using Gaussian white noise, but in the reality, the noise might also be changing in time its properties. It might be dependent on the state of the system to not just be a constant strength, but be correlated in time. It might also have some memory. So a lot of people in this community here have advanced the methods of estimating this critical slowing down in more general systems. What has had a bit less of attention, not no attention at all, but I would say less of an attention is what should we actually expect in the high dimensional case of the climate system, because this is kind of like at least the way it's presented is kind of a one-dimensional framework. So if we have a high dimensional system, we have different ways of measuring the properties of the system by different observables. And the question then is, if you a priori choose an observable to summarize the system, will the fluctuations of this observable actually display the critical slowing down that we anticipate? Or do we actually need some more system-specific knowledge about the actual critical degrees of freedom in the system that allow us to observe a genuine early warning? This hope that an a priori chosen observable will show critical slowdown has been tested in practice with a lot of influential papers where they tried to estimate whether such increase in fluctuations or decrease in restoring rate, for example, can be seen in real-world data, suggesting that indeed the AMOC, which are these papers here on the left side, but also the Greenland ice sheet, the Amazon rainforest, or the South American monsoon are approaching a critical transition. But especially if we want to, as some people do, for example, forecast when this will happen, it would be essential to actually have the exact critical degrees of freedom to use for such an analysis, and not just an observable that seems to be doing well in summarizing the state of the system. So we want to know how, in general, the fluctuations of the system behave in the high dimensional case. So here I'm writing sort of the same equation now, not constrained to having a potential defining the dynamics, but just a general drift A. This is written component-wise, so there's for example, the X component and the Y component and so on here With mu, we also have the noise tensor here, and we have using a sum convention over these indices here. And what we want is we want to know how do the fluctuations of the system evolve as we change the parameter of the system. So the system moves in this for simplicity two-dimensional phase space. Here's a trajectory in purple, but we want to know in general what to expect of the fluctuations. So we want to know what is the probability density over time of the system started at some state x0. And this probability density is of such a system is governed by the Fokker-Planck equation, which is simply governing the probability of the system being in some state x at time t when you started at some state x0. And this is given by this equation with the Fokker-Planck operator here, where here you have the diffusion tensor written down here. And A again is the drift of the deterministic system. Now, this can be formally solved where the probability density is just propagated by some time tau here, and the propagator of this system is called the transfer operator. And if you take this time to infinity, you simply get the stationary distribution of the system here. And the stationary distribution is also the first eigenfunction of this Fokker-Planck operator. And in general, we want to know the first few eigenfunctions of this Fokker-Planck operator because all of the other eigenfunctions will decay very quickly. So the first few eigenfunctions will govern the long-term dynamics of the system. And particularly, we then want to know how does this distribution change its shape as we go towards the tipping point. And by knowing in which direction the fluctuations will go, we can then decide or design observables that capture this change in the fluctuations. Now, as an example, I'm just looking at a two-dimensional system, which is again defined by a potential. And you have two competing fixed points here, one in red, and then the other down here. There is a Bayesian boundary in between here, separating states that go to one side or the other. And there's also a saddle point here. And we're interested at the tipping point that occurs when you increase this control parameter here, and then eventually this fixed point ceases to exist. Here I'm plotting the same potential, but now as contours. Here you have this fixed point here, and if you increase the control parameter here, which are these different snapshots, you will see that the just sampled fluctuations, which are in red here, will at some point become larger and then eventually become large enough to overcome this potential barrier and go over the saddle to the other state. But this only happens over long timescales, and these timescales become longer and longer the lower the noise is. So if you look at lower noise strength and you just look at the fluctuations around the fixed point, you can find that, and this is simply done by actually solving the Fokker-Planck equation and then comparing it also with some empirical samples by forward simulations. You'll see that the density around this fixed point here is indeed widening as it is expected because of the decrease in curvature of the potential, but it's also being stretched in a particular direction. Now, this can lead to a successful early warning of the incoming tipping point, but it can also lead to false negatives because it depends on what are we actually measuring in the system. If we have an observable that measures exactly in this direction here, we will see a large increase in the fluctuations. But if we would be unlucky and happen to be measuring some observable that projects onto this direction in phase space, then we will virtually see no increase in the variabilities. So that we're missing an early warning of the tipping point. And there can not only be false negatives, but also false positives in this higher dimensional view. Now, this is an example of a predator-prey system that was given in this paper exactly to argue the point of missed early warnings in higher dimensional systems, where you have three variables here, and you have a tipping point where at some point the predator, here you have a juvenile prey, you have adult prey, and you have the predator, where the predator population at some point collapses as their mortality rate increases. And here again, you have just scatter plots in a two-dimensional projection of fluctuations around this fixed point up here before the bifurcation. And you can again see that the density changes and generally increases in size, but you can also see that it stretches and it rotates in space. So if you would only observe the predator population and the fluctuations thereof, you will actually see that the fluctuations of the predator decreases as you go towards the tipping point. So this is in some way a false negative too, because you would think all is fine, but it also gives rise to a false positive in the sense that if you, for example, would observe an increase in the predator population, you would probably think that you're going towards a tipping point because you have this critical slowing down, but actually you're going away from the tipping point here. And since we a priori don't know whether we're going away or towards it, this would then constitute a false positive. Now, we want to know basically in which direction can we expect this density to get stretched and skewed, and what are the best observables that we can define from this knowledge, and to see where the largest excursions of this density go to can be viewed with the lens of large deviation theory. So again, we look at the probability density of going to state x from x0, and if you make a so-called WKB approximation, which is basically just an exponential of a series expansion in terms of power of the small noise parameter epsilon, then you plug this into the Fokker-Planck equation, and you only keep the lowest order terms of the noise strength. You end up with a Hamilton-Jacobi equation, which you could solve, but it's also equivalent to it has an associated Lagrangian as well, which is written here with the drift term of the deterministic dynamics here, and the derivative of a trajectory x time derivative. And solving this equation is equivalent to minimizing the action that is defined by this Lagrangian. And this is the so-called Freidlin-Wenzel action. And what now large deviation theory says is that there's a law, a probability law, for a trajectory to stay within some small neighborhood delta of a path x of t. So this is a path of the fluctuating system driven by noise, and this probability is given by the exponential of minus the action. So it kind of exponentially decays with the value of the action on that path. So that means that there should be a minimum value of this action, which is the most likely path, and all other paths become exponentially unlikely. And the actual path that minimizes this action function, that's called the instanton. And the value of this action here that corresponds to this instanton is called the quasi-potential. So it's the minimum of the action of a path that goes from a reference point x0 to any other point x1. And this transition probability then is then defined by e to the minus of this potential. So this is analogous to the actual potential in gradient systems, and particularly if you allow these transition paths to become of infinite lengths, the stationary distribution of the system will be defined by this quasi-potential here as well. Now, what is crucial in sort of the heuristic that we're going to give is that the actual dynamical saddle of the underlying deterministic system, which is sometimes also called the edge state, because it lives on the base and boundary of the system, is actually also a saddle of the quasi-potential, So it's the minimum of the quasi-potential on the basin boundary. So here I used the same system, and I computed the instanton numerically, and you can see that the saddle lies on this instanton path. And I also plotted in some kind of delta tube around this, which is this neighborhood around the instanton where likely trajectories go. So you can see that in the limit of low noise, at least it can be proven for certain cases that this instanton trajectory is actually crossing the saddle point, which means that saddle point, or the edge state edge, I will call it now. One issue is that this is a theory for infinitesimal noise strength, and we don't really know whether this will apply in the real system. And indeed, there have been cases where it has been pointed out that if you still have weak noise but non-infinitesimal noise, this edge state can actually be avoided by the instanton. So what I'm about to say may need to be generalized to not only take into account the edge state, but more finite noise types of minimum action paths that may or may not be computable in realistic systems, but it may be necessary. Now, the crucial point is that this transition probability going from, for example, the vicinity of your attractor to some more far places decays exponentially with the potential difference or the quasi-potential difference from your reference state to the state that you want to go in. So this means if there's a long distance between your state and this saddle point here, transitions will be extremely unlikely. So only if you're close to the bifurcation point where these two states become closer and closer and the potential barrier becomes lower, you will have a significant likelihood of going into the direction along the instanton to the edge state. And it is this directionality of the fluctuations that we want to exploit for observables useful for early warning signals. So if you have a collection of all of your state variables, we propose that you should, at least in the simplest case, could construct observables by a simple scalar projection onto a vector in your phase space. And the suggestion is that you will see a high increase in variance of fluctuations of these observables when you choose a vector that points sort of along the instanton into the direction of the edge state here. So this is the first ingredient. The second ingredient is that we don't want to define an observable using all state variables, but we want to actually find a suitable subspace where we ignore all of the variables where this edge state here or the direction of the instanton is orthogonal. So you have certain variables where the position of the edge state and the attractor are basically the same. And that means the fluctuations in this direction won't change much. So you want to isolate those degrees of freedom where the edge state stands out, so to speak. Going back to the same figures before, where I now plot in the instanton, and I also plot in a vector which points from one of the attractors to the edge state. You can see that indeed this density here becomes increasingly aligned with both the instanton, but also the instanton becomes at some point aligned with the vector pointing directly to the edge state. So if you have knowledge of this edge state beforehand, you could define an observable that is a scalar projection of your state variables onto this vector here, and this will show the largest increase in variability. Now, we tried this in a number of low-dimensional, still not one-dimensional models, but more interestingly, we wanted to see whether it works in a more high-dimensional climate-relevant case. So this is these are simulations with a global ocean, with an ocean-only model. So it's definitely not a state-of-the-art climate model, but it's still a very high-dimensional dynamical system. So we're simulating this in a coarse resolution setup. We're introducing freshwater forcing to the North Atlantic to be able to push the system closer to a tipping point, which is the collapse of the AMOC. And at some point, if the freshwater forcing is a bit higher, we find that there is a coexistence of both a regime where the AMOC is still running and where it's collapsed. So if you take different initial conditions, you can get to either of these states here. And then here you can see how these states look like. This is the overturning stream function, which still has, although weakened, it still has a fully connected AMOC overturning cell. And in the collapse state, you don't have this anymore. There's no transport across the equator of the AMOC in the Atlantic. Notably, even though I'm going to ignore this later, the system doesn't show fixed points as in the simple examples I present, but it's actually chaotic attractors with some fluctuation. So if you start two initial conditions very closely, they will evolve along each other for some time before they become decorrelated. And it has a Lyapunov time of about 5 years or something. So that means more or less after about 50 years, simulations will become completely uncorrelated. Now we use this model and initialized it in very many different initial conditions, but also with different values of the freshwater forcing. And we got a rather complicated stability landscape, where this is now a bifurcation diagram where you have the freshwater forcing as your control parameter, and you have the strength of the AMOC here. Up here are states with a still vigorous AMOC, and down here are collapsed AMOC states. Different colors representing actually different branches of attractors. So you have quite a large variety of different stable states and not just two competing states. But by and large, these in this regime here, at least, these fall into two relatively close bands where you have states with a vigorous AMOC up here and with a collapsed AMOC down here. And later, as we add noise, most of these different states will also merge. So the system comes closer to some sort of bistability. Now, what we want to find is some edge state living in between the AMOC on regime and the AMOC off regime, and then use the properties of this state to define observables that can be used for an early warning. Now, because there are different states, you could also, different pairs of states of on and off attractors, there could also be many different edge states. And this was actually initially what we tried to investigate. But by looking at the basin boundary between different pairs of states, we always only found one particular combination of on and off states where there is actually a boundary. So here's a two-dimensional projection of initial conditions. So these are the dots are initial conditions, and the colors are color-coded according to which attractor they would converge to, which you see the colors here maybe in very small down here. And what we found is that if we make straight lines in phase space, no matter where we would go, we would only find one particular pair of states where there is a transition from an on to an off basin. So we could only find one edge state so far, but there could still be more. It's just what I wanted to say. Now, how do you actually find this edge state? You have to, you cannot just simulate the model forward because it's unstable. But what you can do is you can do the so-called edge tracking procedure, where we make use of the fact that this edge state is a saddle, and thus it is actually attracting all of the states that live on this basin boundary. So what you do is you first try to find states that are very close to this basin boundary, one on each side, going to different initial conditions, to different final attractors. And then you simulate them forward in time. And for a bit of the time, they will follow the basin boundary before they're being ejected transversely to each of these attractors. And then you can, from states which have evolved slightly along the basin boundary, you can again find states that are even much closer to the boundary. And then you repeat this procedure. So you can, with this procedure, you can sort of gradually move down the basin boundary towards the saddle point, and at some point you will converge to something which is then in the vicinity of the saddle point, if not exactly on it. Now we did this for the ocean model, and And what we saw is that if you do this edge tracking, not much happens with the actual AMOC circulation strength. So we start at some state at the basin boundary, which has some weak but intermediate strength of the AMOC. And then we keep producing trajectories that go down this basin boundary, and the AMOC strength doesn't really change. But other properties of the system change quite drastically. For example, here we have a deep Atlantic salinity. They have a long relaxation that it takes until they reach some stationary state here, which is then the vicinity of the edge state. And the property of this edge state in terms of this this observable is that it's actually quite different from either of the attractors. So down here you have the AMOC off attractor, and here you have the AMOC on attractor. So what we did is we looked at all different potential oceanic properties of these states in comparison, and we found that what stands out most, where the edge state stands out most, is actually the deep ocean salinity and temperature in the Atlantic. So here you see anomaly maps of the temperature in the top and the salinity in the bottom of the deep ocean in the edge state compared to the on state and compared to the off state. And what you see is that the most significant feature is that you have a cooling of the edge state compared both to the on state and the off state. And you also have a freshening of the edge state compared both to the on state and the off state. And incidentally, because this happens both at the same time, these two drag in different directions of the density of the water. But what finally happens is that the freshening of the deep ocean leads to a lower density in the bottom waters. And if you decrease the density in the bottom compared to the top, you'll raise the center of gravity of the system, and like this, and you will change the potential energy, the gravitational potential energy of the ocean. This, which can be summarized by something called the dynamic enthalpy. And what we then curiously found is that in the edge state, globally averaged, but especially in the Atlantic, you will have a higher potential energy compared to the on and to the off state. So not only is the edge state some kind of saddle point or local maximum of the quasi-potential, but we have an actual local maximum of the physical potential energy here, which then represents the actual potential energy barrier that has to be overcome when going from one of the attractors to the other. Now, finally, we added noise to the system to see where the fluctuations actually go in the direction of this edge state. This is done by creating some atmospheric noise model, forcing the surface with reanalysis data, derived from reanalysis data. Because the theory is basically designed for low noise, we first wanted to find low noise transitions from one state across the edge state to the other with a rare event algorithm, but we weren't really able to find these transitions. And that's probably due to the lack of an adequate score function that is also needed for these transitions. So at the end, we decided to use higher noise and force the system, even though then we know that the low noise limit isn't really strictly fulfilled anymore, but nevertheless, we want to see whether the typical fingerprint of the edge state is fulfilled. And just to repeat, the typical fingerprint would be a reduction in temperature and salinity of the deep ocean when going from one attractor to the other via the edge state. But at the same time, the AMOC strength will be somewhere in between. And here you see six maps of a number of transitions overlaid on top of each other, where you have north tropical and south deep Atlantic in the upper row temperature and the lower row salinity. And you can see that while in no single observable you will really exactly cross the edge state, all of them show the expected sort of shape of when you have a transition of a decrease in deep ocean salinity and temperature. So this gives some sort of support that maybe we can, even though we're not in a low noise limit necessarily, we can still use these ideas. So then finally, we add medium noise to the system such that we don't observe transitions, but we are going from one parameter value far away from the tipping point to parameter values that are closer to the tipping point. And we see how do fluctuations around the equilibrium that don't make it over the barrier at this noise strength, how do these fluctuations develop in terms of different observables? To look at all different observables or variables of the system would be too much. So we coarse grain in space, looking at salinities, temperatures, densities, but also the stream functions, and then coarse grain them to arrive at about 100 observables that summarize the state of the system. And we want to see, for example, how does the variance or the standard deviation of time series, long time series that are sort of equilibrium slices at these parameter values, how does this change? And here you can see the distribution over this ensemble of observables and how in terms of the increase in standard deviation. And there's a very strong peak at 1. So you see that most observables actually don't change at all in terms of their variability as you go towards the tipping point, suggesting that also most of these observables are not really involved in the bifurcation and are sort of orthogonal to this. And the only observables that really stand out in terms of having a significant increase of standard deviation are actually exactly the ones that we identified as being characteristic of the edge state. So you have a North Atlantic and tropical Atlantic deep ocean temperatures and salinities here. And incidentally, the AMOC strength out of all 100 observables is actually the worst in the sense that it actually gives the strongest decrease, even though only a slight decrease, but still the strongest decrease in variability as you go towards the tipping point. And here this is just illustrated as time series. So if you go from state 1 towards state 4, you see a clear increase in fluctuations of here in this case the deep ocean, North Atlantic deep ocean salinity, and also an increase in the correlation length, temporal correlation. Whereas for the AMOC, you don't see this. You actually see a slight decrease in the variability. Now, finally, this also works sort of quantitatively by if we look at the vector pointing towards the edge state. So if we start in this state 1 here, which is the furthest from the tipping point, you see that fluctuations projected onto now 2 observables, or like a 2-dimensional projection, are more or less independently Gaussian distributed. If you increase the parameter, you can see that they're starting to become larger, the fluctuations. So you have a starting of a critical slowdown, at which point is also the point where we actually estimate the edge state, and we produce a vector that is pointing towards the edge state in some lower dimensional space. So here in this case, it's just as an example, 7 different numbers corresponding to the deep ocean, but also the AMOC here. And as you can increase the control parameter, you can see that this density starts to become stretched and sort of rotates. And then if you're close to before the tipping point, you can see that it more or less stretches and rotates exactly into the direction that is estimated by this vector that we have been determining way before the tipping point in this case. Okay, this was all I wanted to say. I hope it wasn't too long or too confusing. So to summarize, we can use critical slowdown to detect impending tipping points, but I think care needs to be taken in high-dimensional and particularly partially observed systems. We suggest that you can maybe design better early warning signals if you construct observables first by knowing some characteristics of the edge state, or even better, the instanton. But this depends on that you actually have a sufficiently realistic model so that you can estimate these properties. This particular deep ocean fingerprint of the edge state that we found in the global ocean model seems to well motivate what early warning signals could be used for an AMOC collapse. But actually, this is of very limited use because especially in the deep ocean, we have a lack of data and there's very long timescales to establish any sort of statistics. So this is a problem. To potentially alleviate this need for a model, we are currently working on more purely data-driven approaches of detecting the relevant observables by reconstructing these Fokker-Planck eigenfunctions that I mentioned earlier. And also, we want to broaden the framework to more directly deal with the fact that we actually have chaotic attractors and crises instead of saddle node bifurcations and so on. Yeah, thank you very much for your attention.
Thank you so much, Johannes, for this very interesting and dense presentation. I was trying to keep up with the technical information. I hope we have questions in the audience. You are welcome to unmute and ask your questions directly or add them in the chat.
I would have a question, if I can go first. So first of all, thanks very much, Johannes. That was very interesting. And also thanks for cleaning up, sort of in a mathematical sense, cleaning up a lot of things that have been going on in the last years. Regarding the third summary point you have here, is the concern justified that ideally you want to have a sweet spot where things are mathematically precise and still sort of you can apply them to observations, to sparse observations, to observations with uncertainties and so on. Is there such a sweet spot, or do we basically have sort of two disjoint situations in a sense?
Yeah, exactly. This is a very good point. Like I think this is something I still have to work on, or other people, like at the actual statistical problem of what would be the best fingerprint or observable given a certain number of, like a certain amount of data, for example, which is different from finding the theoretically perfect observable. I think there's no issue there as long if you only want to detect that there's early warning signals. I'm pretty sure that there could be such a sweet spot. If it comes to actually predicting when a tipping would happen, I think you would have to have the perfect observable to find the correct scaling. So that's a bit different. But yeah, I think for the first case, one should try to figure out what is the sweet spot. Yeah.
Yeah, but that's really just for the first case, where basically then once we apply this to observation-based data, then the best we can hope for, also including the uncertainties of that, the best we can hope for is statements of the kind saying, over the past X years, stability has declined or increased. But that's basically it.
Yeah, maybe. I mean, yeah. Probably, but of course, there's still the issue. Maybe that we could still be wrong in the sense that we have to be sure that we actually observe all of the possible degrees of freedom, and we also, yeah. So it's I think things can go wrong, but I guess if we have some other strong suspicion that we are going towards a tipping point, we of course have to corroborate this with other evidence.
Yeah.
And I mean the main point here is that of course you can also have a complicated model where you can simulate a tipping point and you can directly observe like what is these things that fluctuations and can change. But I mean, by having the additional knowledge of the edge state, you have kind of a bit more of the smoking gun where you know beforehand which should be the degrees of freedom, and then observing them afterwards gives you a strong indication that this is not a false positive. Yeah.
But if I understand you correctly, then sort of predicting tipping points is a sort of different beast.
I guess so, because at least I don't see how you can really correct for maybe we could think about techniques to correct for the fact that you're not, projecting onto the exact direction, but I wouldn't know whether it's possible. Yeah.
Yeah. Great. Yeah. Thank you very much.
Thank you. We had a question from, I think, Jan Sieber.
Hi, can you hear me, Johannes?
Yeah.
Good. Yeah, so you had these nice pictures of these noise-induced transitions of this model that you had there, and you also had this potential energy, and I didn't quite see. So is one of these the potential energy? In
No.
your previous picture, you showed that the saddle has a higher, call it potential energy. So do these transitions have a higher potential energy in the mean, like when they cross, or lower than the saddle?
I think they do. To be honest, I don't remember whether I have ever plotted this on the potential energy like this. This potential energy is definitely not, when we write this in the paper also, because we found it's definitely not a perfect quasi-potential or Lyapunov function or whatever. So it doesn't strictly decrease along the deterministic paths and so on. But in terms of these transitions, since they kind of follow the reason why the potential energy increases, which is the changes in the deep ocean, I would expect them also to go over this potential energy barrier.
So they have a higher potential energy at their maximum than the saddle.
No, the saddle should be the maximum. You mean the maximum are you referring to something that happens?
So like usually you would expect the potential energy in the ideal case to just start at the low point in the stable equilibrium, then it reaches the maximum at the saddle, and then it goes down again, right? So now how does it look like for these actual transition trajectories? Does it actually go higher than the saddle at its maximum, or does it go?
I should check. I might have checked. I don't know. Like one thing is, of course, here, since we're really not in the low noise case here, that actually all of these, even the attractors sort of shift. So the properties of the system are quite the same. So the fact that the saddle, we seem to be overshooting the saddle here or something. I'm not sure whether it's really a real effect or whether we're just influencing the system by the noise so much.
Yeah. But I mean, still, that makes a remarkable detour all the time. Well, I mean, that's a very noticeable thing.
Yeah. But thank you for pointing out. I should check the potential energy itself, actually. Yeah.
Please go ahead, Sebastian. You have a question?
Yeah, thanks. In the beginning, when you explained critical slowing down in 1D, you pointed out that the recovery rate is more reliable than the variance, for example. And here, I have the impression in your application in high dimensions, you look how the variance change, right? So wouldn't it be useful to combine it also, especially when we don't know about edge states,
Definitely.
but we have changes to combine it with other measures and see
Definitely.
direction.
That's why a bit in the beginning, I maybe said it's not really a method yet. It's just a heuristic. Like at the end of the day, how you measure the critical slowdown, that needs to be optimized, and that's something that I guess the people in this community have worked on a lot, and I have not. But it would be useful to combine. I agree.
Yeah,
this is just about finding the actual which data should you be using to extract the critical slowdown.
Right. It's two steps, right? It's first finding the dimension and then using some indicators, but for both you methods. Yeah, thanks.
One should try to do this.
There's another question. Ryan?
Oh yeah. Thanks, Johannes, for the talk. I found the connections between the early warning signals and sort of the most probable tipping mechanisms quite interesting, and I've never thought about it like that. So it's nice to see. But I have a bit of a perhaps more general question. You were filtering in a lot about the Fokker-Planck equation and its utility and things, and I've always just been a bit doubtful concerning its applicability for high dimensions. So I'd just be interested in your perspective on how powerful it is as a numerical tool, right, versus a theoretical one.
Not really. I mean, I was a bit. I lost a bit track of my narrative at some point. Like first, to be honest, the reason why I was showing the Fokker-Planck equation so in focus is because I'm currently working on methods to actually extract these eigenfunctions from data. But I actually left out this stuff because I got too much material. As you say, as a numerical tool, I guess above dimension of 4 or something, it's really hard to actually solve. So I'm not suggesting that you can do that. Like what I'm doing, I mean, I can just quickly show one picture is that kind of trying to use these ideas because the Fokker-Planck operator, or at least the backward Fokker-Planck operator, will define some observables, and we can try to use data to actually get at these observables. So there's some data-driven techniques to reconstruct these eigenfunctions of the Fokker-Planck operator, and I've tried to do this with the ocean model simulations, and I can see that actually these eigenfunctions correlate very well with the observables that I got. So I think at least this framework can be useful. not actually simulating the Fokker-Planck equations, but kind of the meaning of the different eigenfunctions and also how their eigenvalues change as you go towards the tipping point can be useful.
Okay, yeah, that's a nice part. But I guess I'll ask one more. Literally, what are you using to solve the PDE, just out of interest? In dimensions lower than 5, say, yeah.
No, well, I'm only using it the dimensions lower than 4, but this is the Chang-Cooper method. And anything more specific, I don't really remember because this was done a long time ago.
Yeah. What's that called? I'm not familiar.
The Chang-Cooper scheme or method?
Yeah. Okay, I'll look that
If you
up.
want to know,
Thanks.
I can look up if some more specifics if you're interested. But this is kind of all I can
Yeah, that's
without
fair.
showing some code.
I get scared about solving it for anything higher than 1 dimension, but maybe I shouldn't be so scared,
Okay.
I guess.
Maybe I should be too.
Yeah.
But yeah,
Okay, thanks a lot.
thank you.
We have another question from Matsu.
Hi, Johannes. Thank you very much for your very interesting talk.
Hello.
And I remember that in your 2021 paper, so you proposed that the Veloce model has a fractal Bayesian boundary between the weak and strong AMOCs.
Yeah.
But in your study, yes, this one. So in the present study, you calculated the Bayesian boundary, and it looks like quite smooth. How? Yeah, you can explain it.
So first of all, this was done in a slightly different version of the model. So I'm not sure whether all of the results can be transferred to the other one. But I actually in what I presented now, it just appeared that the boundary was smooth. Like I didn't actually determine the boundary as precisely as in this case. Or that I was taking more like a large scale picture where I looked at different sections in phase space and see where the boundary lies. But the closer you zoom towards the boundary itself, you might discover that it's fractal. I did this sort of edge tracking for a lot of different combinations of states, and in a lot of cases I got into trouble, which are potentially because of a fractal Bayesian boundary, but it's a bit hard to know. The one that I presented and that really worked, there it seems like the boundary was sort of smooth. So you can, because what you need to do in this procedure, you need to take two states and then you need to take the state that lies in the middle and you want to decide whether it goes one way or the other. If you have a fractal Bayesian boundary, it's a bit more difficult, even though not impossible, but it seemed to be relatively smooth. Yeah.
Okay, thank you very much.
Thank you so much, Johannes, once again. Thank you everyone for joining.